get started in just a few minutes here. Again, remember if you keep your videos off and all that good stuff, I would appreciate it. Again, as you come in, remember, again, if you keep the video off and all that, so I don't have so many boxes on my screen, I appreciate it. We'll get started in just a minute or two. Again, if you need to type something or ask a question, make sure you use the chat box. Again, just in another minute or so, we'll get started. All right, so we're going to get started, and I'm sure others will come in as we get going. So we're going to continue lecturing where we left off on Tuesday. And so where we left off really was with Avogadro's number. And remember, Avogadro's number is essentially a conversion factor that we're going to use, but it basically is 6.022 times 10 to the 23. And that basically will equal 1 mole. Remember that Avogadro's numbers in terms of the units can be a variety of units. They can be atoms if we're talking about atoms. They could be molecules if we're talking about molecules. So the actual units that goes with that 6.022 times 10 to the 23 can change depending on sort of the application of it, but that is essentially what 1 mole of something equals. And remember that this is the abbreviation again for moles, so not molecules, so it is the abbreviation for moles. So typically we use Avogadro's number as a conversion factor to go from moles to either atoms or molecules. And really, again, as we talked about at the very end, if you had moles to begin with, we would use Avogadro's number on top. 1 mole would be 6.022 times 10 to the 23. And again, these could be atoms. They could be molecules. The moles will cancel each other out, and you'll be left with atoms. So you'll multiply by Avogadro's number. Again, these could also be molecules if we were using molecules as our unit. And alternative to that, if we had either atoms or molecules or anything like that, we would use Avogadro's number to get to moles. And To do that, if we started with atoms, our molecules, in this case, we would divide by Avogadro's number. So we put the 6.022 times 10 to the 23 on the bottom there. Again, the atoms would cancel, moles would go on top, and we would end up with moles in this case. So we use Avogadro's number really as that sort of conversion factor to allow us to do that, to go from moles to atoms or molecules, sometimes particles, or to go the opposite way, starting with atoms to go to moles, basically. As we talked about at the very end, sometimes people want to use Avogadro's number with like every single calculation they ever do. And again, you shouldn't do that. You should only use Avogadro's number if you're given a number that has atoms, molecules, or particles in it, or you're asked to find a value that is atoms, molecules, or particles. Otherwise, you really shouldn't use Avogadro's number. So we'll come back to the periodic table there. That brings us to another really kind of an important conversion factor that we use a lot, and that's what's known as molar mass. And molar mass is pretty much what the name implies. It's how many grams there are. How many grams there are in a mole of a substance. And when we find the molar mass, it is basically the same as what we were talking about the other day as well. It is essentially equivalent to the atomic mass that we find for a particular element. And molar mass is essentially the conversion factor that we use to go from grams to moles or moles to grams. And that obviously is a conversion factor that we use a lot in chemistry. And that's where I have that periodic table that we just passed. So we'll go back to it. That is where we can also find on the periodic table. So the other day we were talking about this number on the bottom here as being the atomic mass, and that was in basically AMU per atom. But in this application, when we talk about the molar mass, we take that number off of the periodic table, so 1.008, and that is how many grams there are in a mole of hydrogen. I know this periodic table actually rounds a lot. On most periodic tables, when you do pull this number off, usually you want to go to 4 significant figures. I will say this particular periodic table, they rounded pretty in a lot of places, especially on this side. But you can see over here in the middle, 4 significant figures. And that's typically how many significant figures you should take off when you use it from the periodic table is 4 significant figures. That gives us really kind of 2 conversion factors. We could say that there's 1.008 grams of hydrogen in every mole. And the number always stays with the grams part, and it's always per 1 mole when you do the molar mass. Or you can use it as a conversion factor the opposite way. You can say over 1 mole, there's 1.008 grams of hydrogen. So we could use this as really as a conversion factor. You could do that for pretty much anybody that you see here. For example, if we look at iron, that would mean that there's 55.85 grams of iron in a mole. And again, you could write basically the molar mass, which would be, in this case, 55.85 grams per mole. Or again, if you wanted to use it as a conversion factor, you could flip it the other way and go moles over the 55.85 grams. If you were asked what the molar mass of hydrogen was, that's typically how you would give the answer. If you were asked what the molar mass of iron was, you typically would say that's 55.85 grams per mole. Now, molar mass we can also do for molecules as well. It doesn't necessarily have to be just an element by itself. So for example, if we had water, and we can look at water here, which is H2O, we essentially, to find the molar mass of this, we're just going to want to add up pretty much all the parts. So since there's two hydrogens, 1.008 grams per mole, and there's one oxygen, which is basically 16 grams per mole, that would give us a molar mass for water of 18.02 grams per mole. Again, the number stays with the grams, is per 1 mole. We could do that for anything else that you find. For example, if we look over here for CH4, that's 1 carbon at 12.01 grams per mole. And again, all these numbers coming from the periodic table. Again, this one, they kind of rounded a little bit extreme here. Plus 4 times 1.008 grams per mole for our hydrogens there, our 4 hydrogens. So again, if we add all those guys together, basically, we just want all the parts, we get a molar mass of about 1604 for our CH4. And again, that means it's 16.04 grams per mole would be our molar mass. So we could calculate the molar mass for an individual element. We could also calculate the molar mass for a molecule as well. And numerically, as we can see, the molar mass in grams per mole is equal to basically the atomic mass that you find on the periodic table. Any questions on that? So another sort of relationship that sort of ties molar mass together with Avogadro's number is that if we have 1.008 grams of hydrogen, that would equal 1 mole of hydrogen. And as we saw before, if we had 1 mole of hydrogen, that would be 6.022 times 10 to the 23 atoms of hydrogen. So again, that's sort of the relationship between sort of molar mass to Avogadro's number. We could do that for our 85 grams of iron is 1 mole of iron. And obviously in 1 mole of iron, we would have 6.022 times 10 to the 23 atoms of iron. We could also tie the relationship between molar mass and Avogadro's numbers for things that are compounds. So we calculate on the previous page there that there's 18.02 grams of water in every mole of water. And if we had a mole of water, we would also have 6.022 times 10 to the 23. Now, these would not be atoms in this case because water is not an atom, but this is where that unit for Avogadro's number would change. This would be molecules of water. And same thing with our CH4, which I think 1604 off the top of my head. Grams of CH4 equals a mole. And again, if we had a mole of CH4, it would equal 6.022 times 10 to the 23 molecules of CH4. So again, they're all Avogadro's number on this side. We just have different sort of units that are associated with Avogadro's number based on sort of the application that we're doing. Any questions on that there? And obviously for each of these here on the left for our molar mass or on the right for Avogadro's number, you can essentially write 2 conversion factors to use them as conversion factors to do some dimensional analysis. So these are 2 really important sort of conversions that we use in chemistry. So just to summarize here again, we want to use our Avogadro's number to do those conversions that we talked about, going from moles to atoms, our molecules, just like we did earlier. Or again, if we started with atoms, our molecules, we would use Avogadro's number to get ourselves to moles. And again, a reminder, MOL is moles, not molecules. And molar mass, which truthfully is probably the conversion factor you use the most out of these 2. So you'll probably use molar mass a lot more in chemistry than maybe Avogadro's number. We use Avogadro's number occasionally, but definitely molar mass is used a lot. This is what we use to go from grams to moles. Again, our molar mass is essentially our conversion factor for that. So if we start with the grams, we would use the molar mass from the periodic table. We would divide by the molar mass from the periodic table. And obviously here the grams would cancel out, and that would get us moles. And if we started with moles and we wanted grams, we would still use the molar mass, except that we would essentially be multiplying by the molar mass. And the grams would go on top, the moles would go on the bottom, again, also from the periodic table. And again, our moles would cancel and we would be left with grams. So definitely, again, like I said, this one we use a ton throughout chemistry is that molar mass. So general rules, when we pull off the molar mass from the periodic table, usually we want to go about 4 significant figures when we pull it off. And again, the number always stays with the grams part, and it's always per 1 mole on the bottom. And that's very important as well, because sometimes when people start dealing with, especially with equations and reactions, and they see like a coefficient, for example, let's just say we had an equation where we had, say, 2 waters, for example. When we have something like this and you want to calculate the molar mass, it is only from the formula. So you should never, when you're doing molar mass, if you do have something in an equation, do anything with that number that comes in front. You should only look at the formula, and you should only do it based off of the formula. So again, just like we did on the previous page, we would do the molar mass just based off of our 2 hydrogens and our 1 oxygen in this particular case to get our 1802 grams per mole. So very often people confuse when they're doing molar mass. They want to always take kind of the number in the equation into account. And that is for something in a later chapter known as stoichiometry. That's when we take into account those coefficients. So when you do molar mass, it doesn't matter if it's an equation or anything like that. If there's like a 40 in front of it, you just take the actual formula there and use the formula and the periodic table to calculate the molar mass. Any questions on that? Okay. Let's see here. This is what we were just looking at. So there's a lot of sort of relationships here, but essentially this idea of what's on the slide is what we were just talking about, that essentially the atomic mass in AMU is numerically equal to the molar mass in grams per mole. And that basically means that if you need the molar mass of anything, it's always available to you by just simply looking on the periodic table. So just simply looking on the periodic table, that will allow you to calculate the molar mass. And you again could do it based off of 4 significant figures. And usually if you're asked to give the molar mass of a substance, that's usually sort of the understood value that you would give. So each of these represent basically a 1 mole of each of these guys. So we have sulfur, for example, we have iron, we have mercury. And when we think about 1 mole of a particular sort of substance, it may not look in terms of amounts as being the same. So for example, if I took 1 mole of sulfur based on the periodic table, if we went back there to that periodic table, 1 mole of sulfur would be 3207 basically, while if I had 1 mole, say, of copper, it would be 6355. So although they both would represent the same amount of that element in terms of a mole, they do sometimes appear to be maybe more of one versus less of the other. And that's just because 1 mole of sulfur, for example, like we just saw, is 32 grams, while 1 mole of copper would be 63 grams. So this is the relationship between sort of grams and AMU, and you don't have to worry about it. But the reason why they're numerically the same is essentially because the atomic mass is an AMU per atom. That is basically what we get here. That's Avogadro's number, and that's how we would go from atoms to grams. So basically the Avogadro's numbers cancel each other out, and you end up numerically with the exact same value. So this is just our little decision tree here, like we were talking about, and really what we use these for. So again, if we have the grams of the element, we would want to use the molar mass to get to moles. And vice versa, if we have the moles and we want to go to grams, we would use the molar mass. Again, it's only Avogadro's number as we go to atoms or molecules, or vice versa. If we're going the other way from atoms or molecules, that is where we want to use Avogadro's number. So let's take a look at an example here. So we want to calculate the number of grams of iron in 15.7 moles of iron. So again here, what we want to think about is, do we need Avogadro's number? And since we are starting with 15.7 moles of iron, the key here is we do not see anything in terms of atoms. We don't see anything in terms of molecules. So in this case, we don't need Avogadro's number. We're basically just going from moles to grams. So that is the molar mass that we need to do that. And we would go to the periodic table and look under iron. And for iron, we would see that it says 5585. And what that means under iron is that is 5585 grams per mole would be our molar mass for iron. We're going to use that as a conversion factor. So since we are starting with moles, we want the moles on the bottom so that they cancel. We want the 5585 grams of iron on top. The moles will cancel each other out. And if we do that calculation here, we would take our grams, which is 15.7, and we want to multiply it by 5585. And we will end up with, as you can see here, 877 grams. I'm sorry, yep, grams of iron. Any questions on that one? In terms of significant figures, sorry, pop that back up there. Yes, you do have to show it, the work, I guess is the question. So on the exam, oops, come back here. That was the next answer. So on the exam, you do need to show, you need to show this work like normal, just in case something happens and you don't get the right answer there. So again, you should always show the work. You don't necessarily have to cross everything out, but you do need to show it kind of dimensional analysis way. Remember, that's sort of how they want you in chemistry to sort of set these problems up. Other questions on that? What I was going to say is, in terms of significant figures, we started with 3 sig figs. This is basically considered a conversion factor, so like an exact number. So our answer ends up with also 3 sig figs as well because of that. So since I sort of showed the next one, let's just talk about it here. So same thing with this one here. We have lithium, and we want to know how many moles of lithium. So again, the process here is we want to figure out moles. And remember, again, that's moles, not molecules. And it has nothing to do with molecules, atoms, or anything like that here. So again, it's going to be the molar mass as our conversion factor. So again, we want to go to the periodic table And as you can see there, it is 6.941 underneath lithium. And that is how many grams there are per mole. So again, we're going to use our lithium molar mass from the periodic table as basically a conversion factor like we got here. Our grams will cancel and we will be left with it. And we're essentially dividing by the 6.941. And that gets us 11.2 moles of lithium. Same thing with the significant figures here. We're starting basically with 3 sig figs. We're going to end with 3 sig figs here. Again, assuming that this is really a conversion factor and an exact number. Any questions on that calculation there? Let's see here. Let you try this one first. So we want to know how many atoms are there in 0.551 grams of potassium. So why don't you take a moment and try that in case you don't have a periodic table handy. Off of the periodic table, potassium is 3910 grams per mole. So see what you come up with, and we'll talk about it in just a second. Okay, so if we look at this, the first thing we want to really figure out, right, is do we need to use Avogadro's number? And the answer is yes, we do, because we're looking for atoms. But remember, in order to use Avogadro's number, we do need to get it into moles. And in this case, we are starting with grams. So we do want to use the moles first, the molar mass there to do that. So we really want to go from grams to moles using the molar mass to do so. And then we want to go from moles to, this case, atoms using Avogadro's number to do that. So if we start with our 0.551 grams of potassium, again, going to the periodic table there and getting our molar mass, we see it's 3910 grams per mole. Again, at this point, the grams would cancel each other out. You don't have to get an answer at this point, but if you did, the answer you would be with at this point is something like 0.01409. I'm just going to take it out to a few digits, moles of potassium, which again is close to what we need, but we want atoms. So we want to make sure that we then use Avogadro's number. And since we're in moles, the moles are going to go on the bottom, and Avogadro's number will go on top. And here we will use atoms because it is atoms. The moles will cancel out. And again, we want to make sure when we do Avogadro's number, since it is in scientific notation, make sure again you're using your exponent button, your EE button, and you will end up with what Jacqueline had there, 8.49. And that's going to be times 10 to 21 atoms of potassium. Yeah. Any questions on that one there? I won't show it that way. Yeah, so the question is, you do not have to do it step by step, but you do have to show the dimensional analysis. So um, to answer your question, you don't have to get that answer in the middle. You could just go straight across there and continue on with the calculation to get to the answer. So you do have to show the work, again, using dimensional analysis. Sometimes people like to get the number in between, but you don't have to get the number in between. You could just continue it through with one big calculation. It's perfectly fine, and you should end up with the same answer. Other questions on that? I would caution you again, as we talked about from the beginning, that if you do get that answer in the middle there, which is perfectly fine to do it sort of step by step, try not to round too much until the very end. Again, if you kind of round pretty strictly on each of those kind of steps, you may be a little bit off in terms of your answer. So that's why, again, in the middle here, I took it to a good number of digits without rounding very much. And to be truthfully honest with you, I just continued on with the number I had in my calculator. It had all the digits when I did the calculation. So if you do it step by step, try not to round too much. Other questions on that? Okay. And what's filled in is essentially what we just did. Hopefully they got the same answer, which is good, I hope. All right. There you go. Good deal. All right, so why don't you try this next one here, which is how many moles of helium are there in 5.46 grams of helium. Helium is 4.003 grams per mole. From the periodic table. All right, so again, here we're looking for moles. We're starting with grams, so no mention of atoms, molecules, particles, so no need for Avogadro's number. So again, we just want the molar mass like we got up there from the periodic table. We want to put the grams on the bottom so that they cancel. Moles will go on top. Again, our grams will cancel. And if we do that, we will get 5.46 divided by 4.003, going to give us 1.36. And again, the units here will be moles of helium. Yeah, you might have got 1.37. Again, it depends maybe on the rounding. Again, if you didn't use the 4.003 number, maybe it was rounded a little bit, you might have got the 1.37. Um, again, if I use 4.003 on my calculator, I get 1.363, which means if we round it to that 6, we probably should keep the 6. But if you use maybe 4.0 or something like that, you might got a slightly different number. It should be okay. Other questions on that? Questions on how to do grams to moles, moles to grams, Avogadro's number? Let's just take a look at a couple of different ones here. I'll put this up here, so if you watch this later, you'll get the answers for that one. Um, We'll just go through here. Again, a reminder, these will be recorded, so you could just come back if you want to kind of see how they're solved. This is obviously a typo. That should be times 10 to the 23 up on top. Let's take a look at... Let's take a look at this particular one here, though, together, just to kind of see how we could do a problem like this. In this particular case, we're looking for how many atoms of hydrogen there are in 72.5 grams of C3H8O. So this is a little bit different. We're interested in just the hydrogen part of it. We're not interested in the entire compound that's there. So at some point, we're going to need a way to go from the entire thing to really just the hydrogen part. And we could actually use the formula to help us do that. So when we look at a formula, we see these numbers that are on the bottom. And again, if there's no number, it's assumed to be 1. These actually represent the moles of each of those guys. So we could actually use the formula itself to come up with a few different conversion factors for this. And that means that we could say in 1 mole of the entire thing, there would be 3 moles of just the carbon from the formula. We could also say in 1 mole of the entire thing, in terms of the hydrogen, there would be 8 moles of hydrogen. And lastly, we could say in 1 mole of the entire thing, there would be, since there's no number there, it just represents 1 mole of oxygen. So we could actually use these guys as conversion factors. We could say in this case, for example, 1 mole of the entire thing over 3 moles of carbon are 3 moles of carbon over 1 mole of the entire thing. And that's going to allow us to go from the entire compound to the individual element, in this case, that we're interested in. And what we are interested in is the hydrogen. But in order to do that, we do have to do a conversion first. We are in grams of the whole thing. All these guys here from the formula are mole to mole relationships, which means the first thing we need to do really is convert these guys into moles. So in order to convert the 72.5 into moles, we do need the molar mass of this whole thing. So if we go to the periodic table, we could calculate the molar mass of C3H8O. And again, we're just going to add up all the parts. So there's 3 carbons at 12.01 grams per mole for the carbon from the periodic table. There's 8 hydrogens at 1.008 grams per mole from the periodic table. And there's 1 oxygen at 16 grams per mole from the periodic table. And if we add all that together, we will get the molar mass for this compound, and it looks like it will be 6009. And again, you want to usually take the molar mass to 4 significant figures. So typically we want to go to about 4 significant figures. Whenever you're asked to calculate the molar mass, that is traditionally usually how many figures you take when you do molar mass, and also how many significant figures you take when you pull it off the periodic table. So you do want to keep trying to do molar mass to usually 4 significant figures. So the first thing we'd want to do is take 72.5 grams of C3H8O. We're going to use our molar mass that we just calculated from the periodic table. We need to put the grams on the bottom so that they cancel. And if I stopped calculation right there, the grams of the entire thing is going to cancel out. And that's close to what I want, but I'm now in moles of the entire thing. So this is where the relationship that we got from the actual formula will come into play, because now we could go from moles of the entire thing to moles of just the hydrogen. And to do that again, we would use it as a conversion factor. So since we have moles of the entire thing on top, we know from the formula there's 1 mole of the entire thing gives us 8 moles of just the hydrogen. And that's the part that's going to allow us to go from the entire thing to really just the hydrogen part, which is what we're interested in this particular case. And if we stop the calculation right at this point, the units that we would be in is moles of hydrogen, which again is very close to what we're looking for, but we are actually looking for atoms of hydrogen. And because that keyword of atoms is there, that is why we need to use now Avogadro's number. And the last part of the calculation here, we can now go from a mole of hydrogen is our 6.022 times 10 to the 23. And again, here, this would be atoms of hydrogen. The moles of hydrogen will cancel out. At this point, what we want to do is multiply everything across the top. So that's 72.5 times 8 times 6.022 to the 23, making sure we use our exponent button. I would hit equals, and then we're going to divide it by 60.09. And that is going to give us, looks like 5.81 times 10 to the 24 atoms of hydrogen in this case. Any questions on any of those steps? So sometimes you may be asked, like in this case, how many atoms of hydrogen? You may be asked how many grams of hydrogen, or how many atoms of carbon, or grams of carbon, or grams of oxygen. So a very useful way to sort of do those calculations is to actually use the chemical formula itself as a conversion factor. Any questions on any part of that calculation there? Okay, so let's take a look here. That's good. They got basically the same number. It's good. All right. So you got a couple here. Why don't you give these guys a go? Again, I'll give you some time to do it. And I'll give you some information. Carbon from the periodic table, 12.01 grams per mole. Hydrogen, 1.008 grams per mole. And oxygen is 16 grams per mole. So see what you come up with here in terms of these two. We're looking for the moles and the molecules of ethanol. It'll take a minute or so to calculate that. All right, so starting with the first one here, we have 23.2 grams of C2H6O, and we want moles. So since we're starting with grams and we want to go to moles, again, we want to go to the periodic table there and get the molar mass. And in this case, we have 2 times 12.01 for our carbon, plus 6 times 1.008 for our hydrogen, and 16 grams per mole for our oxygen from the periodic table. And that gets us 4607 grams per mole as our molar mass. Any questions on how to calculate that molar mass part? And again, it is the molar mass that we need to basically be used as our conversion factor. Since we're starting with grams, we want to put the grams on the bottom. So it's going to be 4607 grams per mole of C2H6O. The grams are going to cancel. So we're essentially just dividing. So we're going to take 23.2 divided by 4607. And that is going to get us 0.504. And again, this would be moles of C2H6O. And that would be the answer there to the top part. Any questions on that one? For our bottom part, we are looking for molecules. Again, this is the keyword here that tells us we need to use Avogadro's number to do that. And that is going to be from molecules to moles. And that's what the first part we calculated. So if we just take the number from the first part there, 504 moles of C2H6O. We could use Avogadro's number. In this case, it's going to go on top. The moles will cancel. So we're going to multiply by Avogadro's number here. And again, make sure you use your exponent button, which is that EE button, that EXP button. And if you do that, you will end up with, we got 3.03 times 10 to 23. And the units here would be molecules of C2H6O. Any questions on any of these sort of calculations? So obviously you need to be able to convert grams to moles, moles to grams. You need to be able to go from grams to moles to atoms or molecules, and backwards. Obviously, if you start with atoms or molecules, be able to figure out the moles or the grams. Any questions on how to do any of those calculations? Okay, so then let us continue on then. I grab the right thing here. Drag some things out of my way. All right, we'll skip that one. The next thing we're going to talk about is percent composition by mass of an element. So when we calculate the percent composition by mass of an element, it is pretty much what it sounds like. You basically take the mass of the element in that chemical formula, and you divide it by basically the molar mass of the entire thing, and you times it by 100. So if we look at the example that we got here, which is our C2H6O down in this spot down here. And if we wanted to calculate the percent composition of each of those, we basically would first want to calculate the molar mass, which I think is actually what we just did on the other page, grams per mole. And what we're going to do is basically take the grams of each of those elements in that particular formula. So since there are 2 carbons, we would take 2 times the molar mass of carbon from the periodic table, and we would divide it by the molar mass of the entire compound here, and then obviously times it by 100. And that tells us that this compound is basically 52% made up of carbon by mass. We would do the exact same thing for our hydrogen, except that we do have 6 hydrogens in this guy. So we would go to the periodic table and take 6 times the molar mass of hydrogen from the periodic table. So again, this is basically from our periodic table, the molar mass. And same thing down here, this 1.008 is our molar mass of hydrogen, times divided by 4607, times it by 100, and we get 13.13%. And that tells us by mass, this compound is made up of about 13% of hydrogen. At this point, because the only element left is oxygen, you could actually figure out the percentage of oxygen a couple ways. One way is, you know, that since this compound is made up of only carbon, hydrogen, and oxygen, that makes up 100% of the compound. So if you add these 2 guys together and then subtract it from 100, that will give you your percentage of oxygen, basically. We take 100 minus the percentage of carbon in this case, minus the percentage of hydrogen. That could get you the percentage of oxygen. Or you could just do the calculation like the other 2 and take, since there's only 1 oxygen in that compound, the 16 grams per mole from the periodic table, divided by the 4607, which is the molar mass of the entire compound, and that gets you 34.73% of it being oxygen. Obviously, just like we can use 100% here to figure out that last element, when you add up all these percentages here, it should be about 100%. Yeah. And if it doesn't add up to 100%, that means that obviously you're missing an element somewhere. And when we talk about adding up to 100%, it doesn't have to be perfect, like 100% on the nose. It can be just a little over 100%, just a little under 100%, but it really should be in that ballpark, pretty close to 100%. Any questions on how you calculate the percent composition by mass there? Okay. And as we can see there on the bottom, again, it should add up to about 100%. That would tell you, obviously, that you got everything that was there. So the next thing that we're going to talk about really is calculating the empirical formula. And when we calculate the empirical formula, and we're going to talk about how to calculate really 2 types of formulas, both the empirical formula and the molecular formula. I'm actually going to do, I think, is, hang on 1 second here. Grab something just to write with real quick. Okay. There we go. I'll put it back up there in just a second. Just give me 1 second here. Perfect. So pop that back up, I hope. Let's do that. Technology did not like what I just did. Let's try that one more time here. All right, let's see if that fit there. There we go. All right. That hopefully should have worked. All right. Now let's grab something to write with. All right. So what we're going to talk about now are how to calculate two different types of formulas. And the two types of formulas we're going to talk about, one is the empirical formula. And the empirical formula is the simplest whole number ratio of what's present. And that's different than, say, the molecular formula, where the molecular formula tells us exactly how many elements are there, how many atoms of those elements are present. And really, the empirical formula is sort of that simple ratio, whole number ratio of what's present. So, for example, if you had hydrogen peroxide, H2O2, that would be your molecular formula. And basically, that hydrogen peroxide is 2 hydrogens for every 2 oxygens. And that's the same as a 1 hydrogen to 1 oxygen ratio. So you could reduce this down to HO, which would be the empirical formula, which again is basically the simplest whole number ratio of what is present. If you had, say, C2H6 as the molecular formula, you could reduce that down. That's basically 2 carbons to 6 hydrogens. And that's the same as 1 carbon for every 3 hydrogens, right? So the empirical formula would be CH3 in this case. Now, sometimes both the molecular formula and the empirical formula are the same. So for water, for example, this would be the molecular formula, and that's basically 2 hydrogens for every 1 oxygen. You pretty much can't go any lower than that, and that would be both the molecular formula and the empirical formula as well. Most ionic compounds that we come across, those formulas that we see are the empirical formulas. And if you remember, for ionic compounds, or as we'll talk about, essentially when you put a positive and negative guy together, it needs to equal 0 in terms of the charge. And the simplest way to do that, and that's why basically all ionic compounds are really empirical formulas, because when we put them together correctly, it always is put together in the simplest way to get yourself to 0. Now, when we calculate the empirical formula, there's some steps to do this, and it's outlined on the next slide. But the steps to actually calculate an empirical formula is, if you're given everybody in the percent composition by mass, like we were just calculating, the first thing you want to do is convert those into grams. And a good way to convert a percentage into like a number is to assume that you have 100%, are basically 100 grams. And if you assume you have 100 grams of something, what that essentially does is basically turn the percentages into grams using the same numbers. And once you have everybody into grams, the next thing you want to do is convert those grams into moles. And again, to do that, like we were just talking about, that is the molar mass as to how we do that. Now, what you're going to get at this point is moles of each element. And after you have converted it into grams, convert the grams to moles, the third thing you're going to do is divide by the smallest number of moles. So for example, let's say we ended up with 2 moles of A and we ended up with 4 moles of B after we did step number 2 here. What we would then want to do is divide everybody by the 2 moles of A because that is the smallest number of moles. And what that would give us for A is 1. What that would give us for B is 2. And that would be the empirical formula for this made up compound, which would be AB2. And that would be our empirical formula. And it would be our empirical formula because we got all whole numbers here. And if you do this step where you divide by the smallest number of moles and you do get all whole numbers, then that, much like our example here, will give you the empirical formula. But if you do this step and you do not get all whole numbers at this point, then that is not a good thing, and that will not give us our empirical formula. So for example, if we go back and say we ended up with 2 moles of A, but we ended up, say, with 5 moles of B. In this case, we would still divide by 2, which is the smallest. So when we divide by 2, we end up with 1 for A. And when we divide by 2 there, we end up with 2.5 moles for B, which would give us an empirical form of AB 2.5. And there's a problem with that is you can't have like a half a mole of something, right? Or a half of atom of something. So because we did not get whole numbers at this point, and it does happen, you need to fix that. And the way that we fix it is we try to figure out a number that we can multiply that by to get us to basically a whole number. So for example, if you take 2.5 times 1, that equals 2.5. You take 2.5 times 2, that equals 5. That is a whole number. So what we would want to do in this case is take that factor, which is 2 in this case, and multiply not just the B by it, but we want to multiply everybody by it. And if we did, that would give us an empirical form of A2 B5, which is all whole numbers. And that would be the correct empirical formula. So sometimes when you get to this sort of last step, when you divide by the smallest number of moles, sometimes everything's all good. You end up with nice, pretty sort of whole numbers. And sometimes when you divide, you don't get these whole numbers. So in that case, you do need to find a factor to multiply everybody by to basically get to a whole number. So the question usually is like, how close can it be to round or not round? So usually in these type of cases, when you're doing like a textbook type of problem or a homework problem or even a exam or quiz type problem, typically speaking, it needs to be extremely close to the whole number to round. So for example, say you got like 0.998 or 0.98, something like that. That's pretty close to the next number. Or if you just were over the whole number, so maybe you got like 1.01 or 1.02 or something like that, then it's okay to round. But typically speaking, if you get numbers when you divide that end up like what we just saw there, maybe 0.5, 0.33, 0.75, 0.25, for example, these type of numbers, when you divide it and you get that kind of decimals, they're too far to round. So you do have to find a correction factor to sort of fix it by, like what we did up here. But again, if you ended up at this point and you ended up with like a 2.98 or something like that, that's close enough to call it 3, pretty much. Yeah. Any questions on that step there? So these are really the 3 steps that you want to follow when you go to calculate the empirical formula. So let's take a look at the next one, which I think is an example here. All right. So not too far on that. Where is that? There it is. So if we wanted to determine the empirical formula of a compound that's made up of 24.75% potassium, 34.77% Mn, and 40.51% oxygen, we would want to follow these steps. So let's go through these steps. So the first thing we want to do is just take a quick look at our percentages here. And when we look at our percentages, they pretty much add up to 100%. And that's good to look at to make sure you're not missing anything in terms of elements or anything like that. So since they do add up to 100%, we essentially can assume here that we have 100 grams. And basically what that means is for potassium, we would have 24.75 grams of potassium. For our Mn, we would have 34.77 grams of Mn. And for our oxygen, we would have 40.51 grams of oxygen. So that's sort of the first step there to convert these percentages into grams. And again, if you assume you have 100 grams, the numbers will stay the same. So the next thing we want to do is use the periodic table, and we want to use the molar mass of each of these. So for potassium, if we look it up, it's 3910. So we're going to go 3910 grams per mole of potassium. For our Mn, it is 5494 grams per mole. And I think I wrote that a little bit too close, so we'll grab an eraser and move that. Get rid of all that there, give it a little bit more room. And if we do the same thing there for our oxygen, we have 40.51 grams of oxygen, again from the periodic table, 16 grams per mole. So this is your basic step when you want to calculate the empirical formula. You just want to take the grams of each of the elements, and we want to convert them into moles using the molar mass. So if we do that for our potassium, we will end up with 0.633. If we do that for the Mn, we will end up with 0.6329. And if we do that for our oxygen, we will end up with a big number of 2.532 moles of oxygen. Any questions on that so far? So we basically converted our percentages into grams using the molar mass. We converted our grams into moles. Now, the next thing we want to do is take whichever one is the smallest number of moles. And in this particular case, they're pretty close. We're going to divide everybody by the smallest number of moles. So we'll divide everybody by Mn. And we'll divide this guy by 0.6329. So I'll come over here. So for our moles of potassium, when we divide it up here, we essentially get 1. For our moles of Mn, when we divide that, obviously we get 1. And when we divide our oxygen, the 2.53 by the 0.6329, we get 4. And that means that oxygen is 4. Now, since we hit all whole numbers here, we're good. That will give us an empirical formula of KMnO4, which is potassium permanganate. Any question on those steps? So essentially, step 1, convert it into grams. Step 2, convert to moles. And step 3, divide by all the moles. Any questions on where any numbers came from, how we calculated any of that? Okay, so let's see, there might be another one here, I think, for you to try. And what I'll underneath is what I just converted to moles. Oops, put that in the way. So again, I'll scroll through this. Okay, so you want to watch this again. You're bored, you need something to put you to sleep at night. You can kind of see what everything was done there. Let's actually talk about another way that an empirical formula can be found. And it can be found through basically what's known as combustion analysis. And combustion analysis is a way in which we can basically calculate an empirical formula by doing a combustion reaction. And a combustion reaction is essentially when we take something that's organic plus O2, and basically it will make two things. It will make CO2 plus water. And in this type of analysis, what we end up doing is we end up collecting CO2 and we end up collecting hydrogen. And by collecting CO2 and collecting the H2O, collecting water, we're able to determine from that the mass of hydrogen from how much water we collected, and from the CO2, we're able to determine the mass of carbon. And an organic compound is pretty much made up of carbon, hydrogen, and oxygen. So by collecting these things, the CO2 and also the water, that allows us to figure out how much carbon was originally in there. It will also allow us to figure out how much hydrogen was originally in there. The one thing it will not allow us to figure out is how much oxygen was originally in there. And that is because in addition to our organic compound that's going through this reaction, we are adding basically oxygen as part of the reaction. So some of the oxygen that ends up over here on our product side came from this oxygen here. And if we're doing the empirical formula, we're really interested in the oxygen that's right here. Just kind of circle it. So the reason why these two guys are important is because we can find the mass of the oxygen that was in the original compound by taking the mass of the compound minus the mass of the hydrogen that was collected minus the mass of the carbon that was collected. So we have to do the CO2 and the H2O basically to calculate the mass of hydrogen and the mass of carbon that's there. And then we can subtract it from the mass of the compound to basically determine the mass of oxygen was there. It's at that point, once you're able to figure out all three of those things, the mass of the hydrogen, the mass of the carbon, and the mass of the oxygen from that calculation, it's at that point it then becomes a regular empirical formula problem, which means just like we did before, you're going to convert the grams to moles. You're going to divide by the smallest number of moles. And then you can get to your empirical formula. So in this type of problem, it's a little more calculation that you have to do before you could actually get to the process of calculating the empirical formula. So since we're getting towards the end, we will stop here for a second just to kind of maybe take a break and stretch and all that good stuff. So a couple of things in terms of lecture and then tonight's lab, just so you're aware what my plan is. First off, I think next week, technically Tuesday is a holiday, I believe. So I will not probably do any live lecture on Tuesday of next week because it is, I think, technically a school holiday. We'll still observe that, I think. And that means the next really live lecture will occur on that Thursday. So that's in April, I think now, right? So we should be like April 2nd, maybe. For a second, I think. So the next real live lecture after tonight's lab will be on Thursday. Again, in terms of labs, you pretty much only have still the study assignment B, and then also the experiment 7 that's out there that needs to be, completed and turned in. Now, because we're a little behind and all that good stuff, my plan for tonight is we're going to take a little break now, and I am going to end this lecture meeting, but I am going to open up the lab meeting, and this time during lab, I am going to continue to do lecturing on these topics and try to get at least into some nomenclature. That way you can hopefully complete the study assignments that technically we're on for this week's in terms of lab. So I think after today's lecture right now, you probably can start working through, I think it would be study assignment, it's either D, I think, maybe, the one that's units, I think. The study assignment that's entitled units, I think it's about grams, moles, Avogadro's numbers, and stuff like that. So, you should be able to kind of work your way through that. Yeah, I will put an assignment up there for the study assignments for this week. I just haven't done it yet because we just got to it obviously today and stuff like that. They probably won't be due until maybe towards the end of next week. The 2 that were scheduled for this week, which would be the one I think that's units. This should be grams and moles, and then also the study assignment C, I think, which is nomenclature, which is the next topic we're going to talk about as soon as we finish this chapter. So my hope is I'm going to lecture tonight during lab. I'm going to finish hopefully this chapter, hopefully get into some of the nomenclature, kind of put us a little bit back on track. And that means, again, you should be able to probably complete that study assignment D, which is units at this point. So I will put up on Canvas the assignment drop box for you to drop that in. And then also when it would be due, I'll let you know. That just to kind of get us back on track in terms of lecturing. So if you want to pop back in for lab, we'll take a little break and you could keep listening live. If you can't, or whatever your choice is there, again, I will post it up online in the next day or so, and you can listen to it as well, just in case you can't hang in there for the lab part. Any questions on anything happening? I believe, if I'm not mistaken, study assignment B should be due pretty soon, I think. Yeah, maybe next Tuesday. So make sure you get it in by then. Yeah. And then experiment 7 is due April. I forget whatever the date was online, but April something. That one is due. And again, that experiment 7 is a formal lab report. So you got to have a type lab and pre-lab, post-lab, and the carbon pages with the calculations in the lab report as well. Any questions on anything before we take maybe just a little break here before we start up? Okay, so we'll probably start up lab around normal time, maybe about 7:10, and we're going to continue on from this point, talking about the rest of empirical formulas and molecular formulas, and then we'll probably delve into some nomenclature as well, so how to name everything. Any questions on anything? All right, so I will see you in lab if you're coming that way. If not, I'll catch you again. The next live lecture will be next Thursday, as again, Tuesday is technically, I think, a holiday. Good question. I'm not sure how long lab will be. At some point, I'll probably stop. Yeah, so I'm not sure. My goal is probably not to go the entire 3 hours, obviously, but it will probably take a little bit of time to finish the rest of this chapter, and then I would like to get a little bit into nomenclature just to kind of set us up for next week to try to get a little bit back on track. Any other questions on anything? Okay, so again, I'm going to stop this one. That will have some separate sort of recordings. And again, if you're coming back to lab, make sure you go back through and click through the lab one, and then we'll start at about 7:10-ish or so, okay? Otherwise, have a good night if you're out, and I'll see you in a bit for lab at about 7:10.